So it looks like the results from the previous video are slightly more general. Now ABC is a Poncelet family. The dotted triangle is a Poncelet family interscribed between an outer circle and an inner ellipse caustic, okay? It can be any old inner ellipse caustic. I have a mechanism here called Blaschke products that I can actually basically easily find what is an inner ellipse that alongside the outer circle subtends n equals 3 Poncelet family. So just take, for the sake of the explanation here, a circle and any old caustic, which is an ellipse, and that subtends or admits a n equals 3 Poncelet family, here represented by A, B, C. So recall in the previous example, we're using the caustic was a circle, okay? But now it's any old ellipse. Okay, now what I have here also is, as before, the projected image or projective image of ABC under this 3x3 projectivity where these two entries here are 0, no translation, and I can actually set via these controls here values for these 6 free parameters. Okay, so if I play around with the parameters of my projectivity, I get a different A prime, B prime, C prime. Okay, so I'm just showing what happens in when I do this. Okay, now the other component I have here, as before, is a particular triangle center, in this case, the barycenter, not of ABC, but that, in this case here I'm putting a prime, but of A prime, B prime, C prime. Now, one thing I did not mention in the previous video is that via a paper by Hellman and colleagues, and I'll put a link in the description, we have shown that for any Poncelet system, any Poncelet family, the locus of any triangle center, which is a fixed convex combination between x2 and x3, is an ellipse, or is a conic. So, we know that A prime, B prime, C prime over the ABC family, so the projection of the ABC family is also Ponceletian. So the family A prime, B prime, C prime is obviously Ponceletian because it's related to ABC via projectivity. And we know Poncelet is a projective statement. But let's keep going here, right? So now I have the locus of x2, x2 of the barycenter for A prime, B prime, C prime. And as before, what I'm going to do is I'm going to apply a rigid rotation to the caustic with respect to O. Okay, so I have this control here on the left, alpha, that allows me to rotate the center of that generic caustic, which is a nested ellipse, about O. The effect here again is, since the outer conic is a circle, this is as if I was rotating the entire system rigidly, right, about O. Rotation of the outer circle about its center, it's itself. So, one way to think about this is that I'm rotating this entire system about O, or simply rotating the caustic. Now, as before, I want to know what the locus of x2 over a complete revolution of the family, how this locus varies as I rotate the caustic. So as I rotate the caustic. So let's go ahead and animate the caustic. Okay, here we go. So I'm animating the caustic. Caustic is rotating about the center O. And I'm just observing what's happening to the locus x2. Now, as before, all the properties that we saw before when the base system was bicentric will continue to manifest here. So we're generalizing that. Look, the product of the axes, before we're looking at the area, is variable. The ratio of the axes is preserved. And now I'm also reporting the angle of, say, the major semi-axis, and it's also being preserved. So you can see here that all these x2 loci, they don't rotate. Okay, now what happens to this locus if I zero out the elation entries, the two bottom entries? As before, now we get that the locus of x2 in this generic caustic case preserves both area and eccentricity, so both product and ratio of semi-axes. All right, now let's switch to the circumcenter, x3. As before, when the two bottom entries were 0, let's go ahead and change a little bit the values here to get slightly bigger guys or different location. But as before, when the two bottom entries or two relations are 0, the locus, the set of loci of x3 of the projected image gives me preserves product of axes or preserves area, but it does not preserve eccentricity. If those entries, either one of those entries is not 0, then this example with the locus of x3 does not preserve anything. You can see that all these values are variable. Finally, let's go to x4. As before, if you're looking at the set of loci for the orthocenter, as before, as in the bicentric base family, I'm preserving the ratio of semi-axis lengths or the eccentricity. I'm not preserving the area, and I'm preserving the orientation. Okay, so let's see if this is the case. If I change the caustic, let me stop this animation. And you know, these two points here, F1 and F2, they refer to the Blaschke product thing that allows me to sort of flexibly change the caustic. Doesn't matter how I'm exactly doing this, but that's got a different caustic here. For example, something like that. Okay, and let's see if the phenomena continues. So now I know, consider this is my caustic. I can rotate this now, different caustic. Let's orient it differently. Let's orient it like so. Okay, so here's my new caustic. Just, you know, I'm just picking it randomly here. Here's a new caustic. It doesn't matter what it is. Maybe I want to do it like that. Make it more vertical, like that. More, you know, I just want to say that for any generic caustic, we're going to verify those examples. So let's run through them again. I'm going to go back to x2. Again, for this rigidly rotating caustic, you can see here that it preserves the ratio of the axes, the orientation of the axes. Okay, if I zero out my elations, it becomes an affinity, it preserves everything. I think this is a trivial one to prove because everything is very linear here. Now, if I go to x3 and I have an affinity, it preserves the product of the axes, therefore the area. If I don't have an affinity and I have a general projectivity, it doesn't preserve anything. Finally, for x4, if I have any projectivity, it preserves the ratio of the axes. That is to say, the eccentricity, and also preserves the orientation of the axis. So there you have it. The results shown in the previous video, based on a, you know, when the caustic here was a circle, so we had a bicentric, can be extended for the case of any caustic that subtends an n equals 3 with respect to the outer circle. All right, thank you very much.